Okay, welcome. So this is going to be just a quick video on the Warburg impedance derivation. So as a reminder, we've been using electrochemical equivalent circuits to try to understand electrochemical systems, right? The particular tool that we've been using is electrochemical impedance spectroscopy, and where we can identify that the double layer we can kind of approximate as a constant phase element or a capacitor. That's this one here, right? This kind of element. We can identify the solution or uncompensated resistance or series resistance here, just using Ohm laws. Is pretty simple. And then one that we talked about with kinetics is the kinetic charge transfer resistance. And we've mentioned kind of that's in series with the Warburg impedance, which I have said is kind of related to semi-infinite diffusion. But today we'll derive kind of this section that's circled right now, mathematically why that behaves the way it does for this particular case, what we call semi-infinite linear diffusion. Okay, just a reminder, we're talking now about different types of mass transport that are usually described as flux to a system, Ni. So there's three different types that we discussed: convective or bulk flow, which is driven by differences in pressure or the density; diffusive, which is mass diffusion, which is the one that we'll be talking about today and deriving today, where the flow is driven by concentration or temperature gradient. Today we'll be discussing concentration driven. And then specifically, this element called the Warburg element is, as we mentioned, used to describe semi-infinite, and I'll define what I mean by that, and then linear, right, meaning in basically one x direction, diffusion. We also mentioned migration. We're not going to discuss that today, but it's diffusion driven by potential gradient in the solution. It's only going to affect charged species, and it's going to be kind of insignificant if there's large amounts of supporting electrolyte. We'll talk about that a little bit more in lecture 9. So when we have a diffusion limited rate, this kind of continued from some stuff we talked on lecture 8. Basically what we're saying here is when kinetics, so the reaction kinetics, are fast, right? That's essentially what we're talking about. The rate is limited by diffusion rather than by the kinetics. What was going to happen is if we have some electrode surface, right? So what we're plotting here is really the concentration in this y-axis, but at x equals 0, right? This is essentially, you can visualize it. There's an electrode here, and once an oxidized species reaches the electrode, there's going to be an electron transfer, right? And it's going to form a reduced species. So there's going to be a reduction that's occurring. And we're essentially, the thing that's happening is that now, because this oxidized species is being reacted electrochemically, its concentration at our electrode is going to be low, and the concentration of the reduced species is going to be high, right? But then the bulk, there'll be some bulk concentration of the reduced and oxidized species, and there'll be this gradient that's kind of bringing the oxidized species in, right? The oxidized species is going to want to go in this direction. The reduced species is going to want to go in the opposite direction, with the gradient there. All right. So we built up this concentration gradient near the electrode. This specific place, what we're saying, that the rate current is just controlled by how fast species diffuse in or out. Right? So essentially we're saying as soon as oxidized species move to the electrode, they'll react. And then as soon as the reduced species form at the electrode, they'll start moving away. And how fast that diffusion occurs, that's what's dictating the rate. So then the flux for this equation is going to be, the flux of I for diffusion is going to be the diffusion coefficient of species I multiplied by gradient of the concentration of I. Since we're doing linear, this will just be like the derivative of the concentration of I with respect to x, but I'm doing this as a generalized one. And then Ci is concentration of whatever species I. So C ox is the concentration of the oxidized species. Reduced is the concentration of the reduced species. And of course, as a reminder, Ni is flux of that specific species. Right? And so there's a couple different ones. So this concentration will be dependent on time. It'll also be dependent on where you are, how far away you are from the electrode. And so this one with the star here just means the bulk concentration of ice. So bulk meaning far away from the electrode surface. Okay. So you can see this is starting to build up why this would be called linear, right? We have one direction, it's just X, how far you are from the electrode surface. There's no other directions. And it's kind of, basically you can go infinitely far away from, or semi-infinitely far away from the electrode surface. Okay. So this is covered a bit in it's covered extensively in Barden-Faulkner 8.2.1. I just want to mention we are dealing with planar working electrodes. So these are flat electrode surfaces. There's no pores or anything like that. And then there's an unstirred solution, which means that there's no convection. And what we start with is that there's this oxidized species present at some concentration. This one is the bulk concentration. The reduced species is at its own concentration. And this is, governed by a fixed second law of diffusion. Right, as we mentioned, these concentrations of these species are a function of not only time, so where they are near the electrode, how close they are to the electrode, of distance, x, where they are, how close they are to the electrode, but also, there's a time component, location, right? So the time derivative of the concentration of the species is equal to the diffusion coefficient of that species in the solution. And then the second derivative with respect to distance. So in this case, it's just the second derivative with respect to x, right? How far we are from the electrode. And we have one of these for the oxidized species, one of them for the reduced species. And the boundary conditions for this, the one, we're saying that at time t equals 0, so when we start the reaction, anywhere in space for all values of x, the concentration of the oxidized species, right, specifically only at t equals 0, this is going to be equal to this bulk concentration. We just say when we start, this is what we're starting with, and then also the reduced species will be, reduced, right, these values here. In addition to at time t equals 0, this being the case, as x goes to infinity, so basically we're saying as we go infinitely far, semi-infinitely far from the electrode surface, this will also be true for all time. So no longer, if we're running this for a very long amount of time, as long as we're far enough away from the electrode, the concentration of the oxidized and reduced species will be this bulk starting concentration of the species. Okay. The other thing we're going to assume, right, is that kinetics are so fast that essentially if the species reach the electrode surface, they can be reacted. They instantaneously react. So basically what this means is if you're diffusing an oxidized species to the electrode surface, as fast the flux of it diffusing, all of those species that are hitting the electrode basically going to be reacted instantaneously, right? This is not an assumption we want to make always, because sometimes the kinetics are slow, but if the kinetics are fast, that's what we can assume. So at the electrode surface, we have the diffusion coefficient of the oxidized species multiplied by, right, at the electrode surface, x equals 0, the derivative of the oxidized species concentration with respect to x, plus the diffusion coefficient of the reduced species times the derivative of the reduced species concentration with respect to x at that same location is going to be equal to 0. So basically, there's no discontinuity here. Right, so oxidized species are going to be, in the case that we drew it, oxidized species are going to be coming to the electrode surface. Reduced species are going to be going away from the electrode surface, right? Because of this gradient is going to have an opposite sign. So that's why there'll be a bounce here and they'll be equal to 0, right? So this will be different signs here. If we have some current as a function of time, so some I of t, current is a function of time, then that current, as we've defined it, would just be, okay, the diffusion coefficient of the oxidized species times C ox x of t dx, right? Basically the flux of the oxidized species to the surface, or negative the flux, is equal to the current, right, as a function of time, divided by NF, coming from Faraday's law, and then A. Because actually the flux is going to be have this extra units of area. So directly it should be compared to the current density. So we have to divide by A, right? And that's just from Faraday's law. The NF is from Faraday's law, right? Because we have a certain amount of moles of things hitting the electrode surface, and we want to convert it to a current. Faraday's law is how we do that. And we can see that this is, in this case, is going to be negative because the oxidized species coming to surface will be reduced, right? So that would tell us that we'd want a negative current. So the sign there would be different because we're using, might be different than Texas notation because we're using IUPAC notation here, right? So we have this one, and then of course we can just see that we have the exact same equation. I'm not going to write it again, or very similar equation. From this, we can relate it to the reduced species concentration. So what we're going to do with this equation, now we're relating the current to these this concentration gradient, the diffusion coefficient. We can take the Laplace transform of that and convert t to this unit s, variable s. The diffusion coefficient of the oxidized species, d, and then the c bar is just because representing that we took the Laplace transform. So now, rather than being in the, a function of x and t, it's now a function of x and s. Still the derivative with respect to x. At x equals 0 at the electrode surface where the reaction is occurring instantaneously, negative is divided by NFA, right? So this Laplace transform that we took. So with that, now we're going to try to basically solve for this concentration of the oxidized species. And remember, we have a corresponding one for the reduced species as well, right? Just from this relationship, right? We can get the same thing. So we're just going to take the derivative, sorry, the integral with respect to x to basically back this out here. And this is what we'll get, that the this will be this constant, right? That's at kind of infinite distance away. The bulk concentration of the oxidized species over S, plus this current as a function of S divided by NFA from this portion. And then we've basically gotten rid of this dox, or so we have the square root of the dox term, right? This diffusion coefficient term, square root of S, and then the exponential of negative S over the diffusion coefficient to the 1/2 times x, just taking basically the integral to solve this equation. So we have a very similar one for the reduced species. The difference is going to be this negative sign here, right? From taking that, because there'll be, right, they'll be from this portion when if we wanted to use this equation here, right, and replace it with reduced species, we know that negative reduced species, and then its derivative is going to be equal to positive of the oxidized species. Okay. So we have this, right? And we know that at x equals 0, so basically at the electrode surface, this exponential at x equals 0, this exponential term will go to just 1, right? Both of these, right? So what we'll end up getting is that we can rewrite this a little bit simpler. Cox x s is this equal to this bulk concentration over S plus, right, this I of current NFA, the square root of the diffusion coefficient times the square root of S right? And then the exponential term just goes to 1, so we just have a 1 there. Then we have a similar one for the reduced species, xs, right, bar equals the bulk reduced species concentration, or the initial one, both, it's the same, it's in the initial concentration, also the bulk concentration, minus IS over NFA, the diffusion coefficient for the reduced species, square root of S. Yeah. There's a few more details and kind of some of the math that is done actually in 8.2.1 in case you're really curious or you don't remember some of the math there. As I mentioned, there's this switch sign, right, in BARD in chapter 8 and 10 because of how reduction is defined, whether it's, you know, a negative current or positive current. So just if you're confused about the sign, it's, double check which notation is being used. So now we have this, and for a specific set of conditions, remember, for our initial conditions that we talked about before, at time t equals 0, right, we have these species. We can solve for these equations here, and we get the results that at x equals 0, so at the electrode surface, for any time using these initial conditions, and basically using inversion by convolution to get back into time units rather than s units, we get that it's going to be the electrode surface is going to be something related to the bulk concentration, 1 over NFA, then the dox, so the diffusion coefficient of the oxidized species, to 1/2 pi to the 1/2. That's right. This is what's on this portion here, and then this integral here is coming from this inversion by convolution, where, just to be clear, this is a function. So it's the current as a function of t minus u. It's not the current times t minus u, right? And then divided by u to the 1/2, the integral of all of that with respect to u from 0 to time t that you're interested in, right? So this time t, this time t. And we have a similar one for the reduced species. Just again, the minus sign is the major difference there. Okay, so this might be look a little tricky. How do we actually get to this? So we know for our specific condition, right, we're thinking about solving this for electrochemical impedance spectroscopy. So we know we have an AC current, right? And the AC current, we'll say it has the form of the current is some I0, some current amplitude times sine of omega, its frequency times t, right? Because the sinusoid is basically our current. And there's a trig identity where the sine of omega times t minus u, right? So here is just sine omega t cosine omega u minus cosine omega t sine omega u, right? So this is just a trig identity for the sinusoid that our current happens to be in. So when we're trying to evaluate this integral here, which shows up twice, it shows up in both of our equations. Yeah, that's what we have here. We can just say that, well, we know our current is going to be a sinusoid, right? So it's going to be I0 times sine omega, and then, right, normally we'd have omega t here, but now it's a function of not t, but t minus u. That's where this comes in here, right? And then we can apply this trig identity to basically say that our integral, this integral here, is going to be I0 sine omega t, and then the integral of from 0 to t of cosine omega u divided by u to the 1/2 du, right? Because u is the variable that the integral is doing, minus I0 cosine omega t, and then the integral from 0 to t of sine omega u divided by u to the 1/2 du, right? So it's basically just taking this portion here, yeah, using that, putting that into our integral, and then we get this this integral here that we're using. Okay, so that's just this boxed. That's basically just what this boxed section is. It's not the full equation yet, but it's just kind of helping us solve that boxed equation. Okay, so remember, we're using this AC current for electrochemical impedance spectroscopy, which is giving us a sinusoid. And then what the assumption we're going to make is that we're doing no net electrolysis. So, right, we're having the sinusoid and there's no net electrochemical reaction, just kind of oscillating back between whatever we reduce, then we're oxidizing, going back and forth there. So when we do that, in this particular assumption, we're going to assume that we reach some steady state, right? So some time goes to infinity. And then we have the integral of this particular case for the integral that we talked about here. We're going to divide up into this portion. Now, instead of t is going to be going to infinity, we can basically do that a little bit more simply from an identity here. The integral from 0 to infinity of sine of some, any variable x, x to the 1, divided by x to the 1/2 dx, right? This is just defined as, or it equals to pi over 2 to the 1/2, right? So all we're doing is we're taking this information, we're saying, okay, we're going to substitute this x value for omega u, and we can solve. This integral is just going to end up being pi over 2 omega to the 1/2. This one is going to be pi over 2 omega to the 1/2, right? Using these identities. We're going from 0 to infinity, so we'll have a similar one for cosine and sine. And then we can say that this full integral that we had originally, when we're specifically at steady state, so that there's no net electrolysis, so no net reaction occurring, this is going to be equal to this I0 pi over 2 omega, our frequency, to the 1/2, and then we're going to lump things so that we have our sine omega t, right, this sine omega t, minus our cosine omega t, right, because these are the same, we just pulled them out from there. And then they both have this I0 term, so we pulled out everything there. Okay, so again, right, that's just this integral here, we're basically just solving for that. For the specific case where our current is a sinusoid, so it's the AC current, which we're using for EIS, and where we have no net electrolysis, we can solve that way. Okay, so this tells us, going back, plugging everything in, right, plugging in, the surface concentration, when we have semi-infinite linear diffusion, that was giving our linear diffusion equations, we have a sinusoidal current with no net electrolysis, we're just plugging this in. So the concentration of the electrode surface is going to be the bulk concentration plus this term related to a sinusoid, the sinusoids, sorry, where we have some of these, this omega and this 2 term, basically that's coming from here. We're just pulling in into this section. The pi is canceling out here, right? Remember we had a pi here, so that one's being canceled out by this pi on top here. That's why it's disappearing. And then we have these 2 expressions for basically, this tells us what's the concentration at our electrode surface at a given time. It's going to be a function of the frequency, so how fast these oscillations are occurring. It's going to be related to the diffusion coefficient, the area of the electrode, the current, the amplitude of the current, and then the bulk concentration. Okay, so if we're thinking about kind of know the concentration, it's also of relevance to us, the flux or the gradient in the concentration with respect to time. Sorry, not the flux, just the change in concentration with respect to time. So we have d c ox of 0t, right? dt equals I0, right? The constant is going away because it's constant with time. Omega to the 1/2. NFA 2 dox to the 1/2 times cosine omega t plus sine omega t, right? We have a similar one, the change in the reduced species, I'm just going to call it R to save a little writing, 0t with respect to time is going to be negative I0 divided by NFA, and then I'm going to write it, let's pull out some of these things. So omega, so the frequency, 2 times 2, divided by 2 times the reduced species diffusion coefficient to the 1/2, and then this one will also be cosine omega t plus sine omega t, right? So all that's happening is we're taking the derivative of these terms. That's where the extra omega is coming out. It's canceling with this omega on the bottom. That's where we're getting an omega on the numerator of 1/2. Okay. So this is just, now we have the concentration as a function of time at the electrode surface, and then the change in the concentration with respect to time at the electrode surface. Just as a reminder, we're using this AC current here. I is equal to I0 sine omega t, right? We also know the change in the current with respect to time is just the integral of that, I0 omega cosine omega t, just taking the derivative of sine omega t will give you omega cosine omega t. And then we also have a voltage, right? That must correspond to this, E. This is our voltage, right? That voltage we're saying is a function of the current that's currently going, the concentration of the oxidized species and the concentration of the reduced species. So the derivative of the voltage with respect to time is going to be the partial derivative, right? The partial derivative of the voltage with respect to the current, keeping, so what this means is, you know, this and this are kept constant, so if those are constant, times di dt, plus the partial derivative of the voltage with respect to the oxidized species concentration, keeping the other two things constant, times the derivative of CO with respect to time, plus the partial derivative of the voltage with respect to the reduced species concentration, keeping the other two, so the current and CO constant. And then that's multiplied by the change in the reduced species concentration with respect to time at the electrode surface, okay? So this might look like a lot of stuff, but we'll notice that, let me get these colors right. We'll notice that this term, right, and this term, we already have here, right? We have this and this, we have those. So those are derived from our diffusion equations, right? So we know what those are. And then these terms, the change in the voltage with respect to the concentration of a reduced and oxidized species, right, are going to be related to, or basically just a derivative of the Nernst equation, right? The voltage is related to the Nernst equation, as the concentrations through the Nernst equation. We're specifically applying under linearizing conditions for Butler-Volmer equation. Okay, so we're just going to start substituting in from the diffusion equation that we solved for this AC input, right? These orange things that are indicated here, right? This equation and then this equation. Okay. So we get that the change in the voltage with respect to time is equal to first, that was one other one I missed, that change in the current, the voltage with respect, this is our R1, if everything else is constant, right? So we get R1, we know that di dt, right? You know that this is I0 omega cosine omega t, so that's where we get this first little section, right? Then we have this change in the partial derivative of the E with respect to the oxidized, the red portion here I haven't done yet, but we do know from our diffusion equations we have, right, diffusion equations here, we can just plug in this term from here, right? And then this term from the other one for the reduced species concentration. So now just plugging in things here. Yeah. And we can say that, let's specifically look at this one. We're also going to say that the partial derivative of the voltage with respect to the change in, with respect to the oxidized species concentration is going to be the partial derivative of, using our Nernst equation, minus RT over NF, right, log of the reduced species over the oxidized species, right, that's the voltage there, yeah, divided by, or the derivative with respect to the oxidized species concentration. This is going to be RT over NF, and then the change in the logarithm of the oxidized species concentration with respect to the oxidized species concentration. And this would be equal to RT over NF times 1 over Cox bulk, right? So specifically, look, where this is coming from is we're looking at this linearized region of the Butler-Volmer-Nernst relationship where we're saying that the over voltage is equal to RT over NF, right? Cox at the electrode surface is divided by the bulk, like basically ratioed to the bulk concentration minus the reduced species concentration at zero at the electrode surface ratioed to the bulk reduced concentration plus I over our exchange current density, right? So this is all kind of, we're using this linearization is how we're getting this final portion where we get the change with respect to the bulk oxidized species concentration, right? So that's this little portion. We have another one for the change in the partial derivative of the voltage with respect to the reduced species concentration. We're going to start plugging all of this stuff in, right? Basically plugging this in for one of those. The only replacement that is that it would have to be either the bulk oxidized species or the bulk reduced species concentration. And we get that this dE dt, right? Sorry, this should be dE dt, the derivative, right? Is equal to all of these things. So just plugging in things again. So we see here, right? This is new, it's coming in. Rearranging a little bit of stuff. I've left a couple things out that I'm just going to fill in. I didn't want to write out the whole thing again, but just what's missing here is that we're going to pull out I0 omega cosine omega t multiplied by all this R1 term, which is basically the change in the voltage, the resistance of the voltage current relationship is the resistance, this R1. And then on here, we're having I0 sine omega t. And just as a reminder, so what all this is equal to is just this dE d time. Okay. So it's rearranging, and we see that in both of these equations, we have this little portion here. Right? We have this portion here. Yeah. And then we have the same value that spits out here. This RT over square root of 2 times NF squared times the area, or multiplied by the area, multiplied by 1 over the bulk concentration of the oxidized species multiplied by the square root of its diffusion coefficient, and then the same thing for the reduced species. So what we're going to do is that kind of highlighted portion that I just showed you, is we're going to define it as the Warburg constant. So it's just a definition, the sigma term, RT, so the ideal gas constant times temperature, NF squared times the area. Sometimes you'll see without the area, but it should be the area in the way we've written it, times the square root of 1 over the square root of 2, and then 1 over the bulk concentration of the oxidized species times the square root of its diffusion coefficient, plus 1 over the bulk concentration of our reduced species times the square root of its diffusion coefficient, right? So this is the Warburg constant, right? This is here and here. Greatly simplifies things. So basically we're saying the change in the voltage with respect to time is going to be this R1 term plus our sigma, our Warburg constant, divided by the square root of omega. That's where it's coming here. So this is all multiplied. This portion is multiplied by I0 times omega cosine omega t. And then we also have plus our Warburg constant here multiplied by, instead of divided by the square root of omega, it's multiplied by the square root of omega, and then I0 sine omega t, right? So we have these two kind of a cosine type term, right? The cosine type term with these portions, and then a sine type term here. Sometimes this portion is kind of called, remember, we have might call it the pseudo capacitance of this portion, right? Where we say it's 1 over sigma square root of omega, right? And this would be the same thing as if we just said that there was a reactance of 1 over omega c, right? So sometimes this will appear as like something that's called a pseudo capacitance. But what we can see from here is, right, we have the I0, right? Our I0 we defined is, sorry, our current is I0 times sine omega t, right? Remember that the change in the current with respect to time is I0 omega times cosine omega t right here. And then we have our voltage relationship. So we're trying to relate, we're putting this sinusoid current in, and there's a corresponding voltage with it. We can see when we're thinking about this particular black box, whatever in there undergoing the reaction, the diffusion component, the resistance component, we can see that if we're thinking about the current, we have an in phase, right? So this is cosine omega t. So this would be the in phase portion, right? And then we have a pi out of 2 out of phase. So that would be the sine portion here. So it'd be like a capacitor-like one. So this is kind of like a pseudo capacitor portion of this. So we could put basically the relationship between the current and the voltage with respect to time in this little black box that we're thinking about is going to have an in phase or a real component that's going to be this value R1 plus our Warburg constant divided by square root of omega, right? And then this imaginary portion, which is also going to be the Warburg constant divided by square root of omega. Because remember that omega term, normally we'd have this omega term that has to show up when we have a capacitor. So that's why it's going from square root of omega on the top to the square root of omega in the numerator to a square root of omega in the denominator. Because for these imaginary terms, we have this omega term that always is there when we're thinking about converting it to the imaginary impedance. So real, imaginary. Okay. And we see that these are identical, these terms, but the real portion has this additional resistance R1 there. Okay. So just a reminder again, we assume that there's semi-infinite linear diffusion transport. So the Warburg impedance that we just derived is specifically the case where there's diffusion, there's charge transfer in series, there's infinite diffusion length, there's no net electrolysis. So our Warburg impedance specifically would be the Warburg, I think it's called constant, Warburg constant divided by omega to the 1/2 minus j sigma divided by omega to the 1/2. Okay. Now, why I've left out the R1, right, is because that R1 term is what we call our charge transfer resistance, or R1, or sometimes we call it RF for Faradaic, yeah? And then this is our Warburg impedance here. So if we look at the entirety of this, like the thing we called the black box before, right, the effective impedance would be RF plus our Warburg term, which is just this, our entire Warburg element, which is the real portion, omega 1/2, minus j, imaginary number j, sigma over omega to the 1/2. Right. So this is the derivation for the Warburg impedance, this 45 degree feature that we see. Modified versions need to be used whenever you're not in infinite linear diffusion conditions. There's a lot of examples like that, and we'll talk about a couple of those in lecture 9. Yeah, just a reminder. So why this, I think this was tricky for people, why this is switching over. Remember, when we're thinking about this out of phase, there's this capacitance term here that this is a frequency term here that's going to cause that switch essentially. Okay, so that's the derivation of this. And if there's further questions, either let me know, or some of the details will be in Bard and Faulkner. But I'll shut this down now and post this.